So how many valence electrons do we have for this molecule? Or how do we determine that? Are we good with 32? 4 for the silicon based off of the position that it's on the table. And then the chlorines, there's 7 and there's 4 of them. So 28 and 4, 32 total. All right, so I'm going to draw a Lewis structure. Who are we going to put in the middle and why? So can you give me 2 reasons why silicon goes in the middle? Say again? Wants to gain 4 electrons? Okay. And wanting to gain 4 electrons allows it to do what? Okay. But associated with this, make 4 bonds. Okay, what about the chlorine? But it's not helpful. It can only make 1 bond, it only needs 1 electron. So one reason is the silicon can make more bonds than the chlorine. What's the other reason? There's only 1 of them. So odd man out is going to usually lead you straight to whichever atom is going to be the central atom. All right, so I've got a silicon in the middle, and a chlorine, and a chlorine, and a chlorine, and a chlorine, and I hook everybody up with a bond. How many electrons have I used when I make a bond with each of these? 8 of my 32. Is anybody happy? The silicon's already happy. It sees 8. So I need to get rid of how many more electrons? 24? Okay, so I've got, there's 6, there's 6, there's 6, and there's 6. So all 24 are gone. Great, so used all my electrons. Everybody's satisfied their octet. And so the next question, the Vesper model. There aren't any electrons on the central atom, lone pairs of electrons on the central atom. So then this doesn't apply. That's not applicable. And then the structure for the molecular geometry is I have one thing with 4 things around it, and it has no lone pairs on it. So what's the structure? Tetrahedral. Okay. Let's move on to this PCl3. So valence electrons. What do we got? 5 for the phosphorus. Okay. And 7 times 3 for the chlorine, so 26 electrons. You good with that? All right. And so for the same reasons that we had before, phosphorus, we're going to go ahead and put that in the middle. We need to deal with 26 electrons, so I'll just put a chlorine here and a chlorine here and a chlorine here, and then I'll connect everybody up. So I've used 6 of my 26 electrons, and nobody's happy yet. So what do we want to do? Put electrons on chlorines? Okay. Great. So all of the chlorines are happy, and I have 2 electrons left. The phosphorus still isn't happy. It needs 2 more electrons, so I'm just going to go ahead and add those there. Alrighty. So what... we didn't draw the 3D structure on the one up here. What's the 3D structure on the silicon look like? It looks like a tetrahedral, right? And so I need a wedge here, and I need a dash here.
So I'm kind of confused as to why, on the first part of it, because the way I'm reading it in this textbook, it's saying the molecular structures are identical to the electron pair geometries when there are no lone pairs.
Yep.
So is the Vesper not applicable because there's no lone pairs?
Yeah.
It's just not part of it.
It doesn't matter because Vesper is about a valence shell electron pair repulsion on the central atom, and there aren't any, so it doesn't matter.
So there always will be molecular geometry. Right?
Always be a molecular geometry,
okay.
Absolutely. And if the central atom has nothing, like in this case, then there's no Vesper geometry.
Okay, because I wrote the same for both of these things.
What you wrote makes sense. Okay, so I'm going to draw the 3D structure for this. And so I've got a phosphorus, and I'm going to put I don't know, chlorine here. Let me do it like this. Chlorine there. I'm going to put a lone pair of electrons up top. I'm going to put a chlorine like that. I'm going to put a chlorine like that. So with the electrons on, what shape do I have? I have a tetrahedron. I have one object with four things around it. Okay, so when I go for the molecular geometry, I go ahead and get rid of the electrons. Now what shape do I have? Keenan. A trigonal pyramid. Okay, and it's a triangle base going up. Why is it a trigonal pyramid, not just a pyramid? Yeah, pyramids have four sides. They don't have three. All right, next one. So I've got myself some, what's this polyatomic ion? Nitrate. All right, so valence, how many electrons am I dealing with? 5 for the nitrogen, plus 6 times 3 for the oxygen, plus 1 for the extra. So we've got 24. Okay. Who are we going to put in the middle? Nitrogen. Okay. So I got a nitrogen here, and then an oxygen, and an oxygen, and an oxygen. So I've used 6 of my 24, and nobody's happy right now. What would you like to do? Where do you want to put electrons? How many electrons do I have left? 18? Okay. So if I threw 6 electrons around each of the oxygens would be a satisfied octet, but I run out of oxygens. So what if I took two electrons, say, off of this oxygen, and I moved them over to this nitrogen? Now the nitrogen's happy, but now the oxygen isn't happy. So we had that situation when we were doing the example for formaldehyde on Monday. So what do? I make a double bond. So I'd force those 2 electrons to be shared, and so I end up with that structure there. Are the octet rules satisfied? Yeah, we're seeing 1, 2, those 2, and those 2, and 2 and 2. So we see 8 there, and same situation for the nitrogen. It's got 4 bonds on it, so it sees an octet. Okay, so what's the structure for this? I've got one central atom, and how many things are connected to it? Only 3 things are connected to it. That's it. Trigonal planar. Is there a Vesper? Nope, nothing on the central atom. So nothing here, and this is this molecule is flat. We okay with that? When we say trigonal planar, all 4 of those atoms will be laying flat on a surface. All right. How about this? What would you call this one here? The SF6. Sulfur hexafluoride? Yep, that sounds good. All right, so I've got 6 for my sulfur, plus 7 times 6 for my phosphorus, or my fluorine. And so 48 electrons. Who are we putting in the middle? My sulfur. So I have a sulfur and a fluorine 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 and a fluorine. And then I'll connect everybody up. And so, how many electrons have I used so far? 12. So I got 36 left. Is anybody happy? Sulfur's like maybe too happy, right? So I'm just going to go ahead and toss on the 6 electrons on each of these. And I have used all 48 of my electrons. Is this structure okay? Why? Sulfur's weird. All right, I don't mind that. Boron, aluminum, and phosphorus and sulfur. What do we know about those four? Exceptions to the octet rule. So the boron and the aluminum want to see 6 electrons, and the phosphorus and sulfur can see more than 8. Don't have to. Like, we had that phosphorus that was up here, right? And this guy saw 8. Didn't need to see. But if I'm forced to put electrons someplace because I can't, I can't add extra electrons to the fluorine, it won't accept it. But the phosphorus would. Yeah.
So boron and aluminum,
they only want to see 6.
Okay, so they can't have 8.
They won't have 8. Okay, so there's my Lewis structure, and then my 3D drawing for this is going to be sulfur, fluorine, 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 fluorine. And what shape do we have with this one? I know my drawing isn't all that obvious, but bipyramidal. It's a box, right? Box in the center. And so then I've got a point on top of the box and a point on the bottom of the box, so I have bipyramidal or octahedral. What were you going to say?
Can you draw it with, like...
If it's got 8 sides, you can draw it however you like.
Okay. Good.
I just draw it like that because it's symmetrical for me. It's easier for me to see it. But if you see it in some other orientation, that's totally fine. So Vesper geometry? Nothing. And this one? Or bipyramidal? All right, how about the PBR5? Electrons? $40. I'll put a phosphorus in the middle. So I've used 10, I have 30 left. If I put 6 around each, I've used all 30 of the remaining electrons. And the bromines are all happy, and the phosphorus is, again, a little bit too happy. So if I'm going to draw the Lewis structure, or the 3D model for this, I have a phosphorus with a boron, a bromine, a bromine, a bromine, and then a bromine going back, and a bromine coming forward. So hopefully what you can see with this is there's a triangle in the middle, and then there's a point on the top and the point on the bottom. So it's very similar to the last one, except instead of it being bipyramidal, it's trigonal bipyramidal, because the pyramids have a 3-sided bottom instead of a 4-sided bottom. So Na, and then ready? All right, so the nitrogen has 5, and I've got 8 total. I'll go ahead and put a nitrogen in the middle, and then a hydrogen, and a hydrogen, and a hydrogen. I've used 6 electrons. The hydrogens are happy, the nitrogen's not. I'll throw 2 more electrons here, and now all 8 electrons have been used, and molecule's happy. So I'm going to do the 3D structure for this. I have a nitrogen, lone pair of electrons, a hydrogen, and a hydrogen. So with the electron on it, what shape do I have? Tetrahedral. Okay, so the VSEPR is tetrahedral. And the molecular geometry? So I get rid of those electrons up top, and then I have just trigonal pyramidal. We already had a trigonal pyramidal. What is similar about this nitrogen and this PCl3? The what? They are, but that's, what about the atoms is similar? How many bonds is the phosphorus typically making? 3. And the nitrogen? 3. Why? Same column. How many bonds is the chlorine making? And the hydrogen? They're both making 1. So they're going to have a similar structure. So if you're looking like, you can guesstimate pretty quickly what the structure is going to be if you already have a structure figured out. If I know that the central atom is making X number of bonds and it's the same number as another molecule I've made and everything around it is doing X number of bonds and those numbers are the same. So because that PCl3 and that NH3 both have a central atom making 3 bonds and the exterior atoms making 1 bond, they're going to have the same geometry. Okay. Ready.